Okay, everyone, we're going to get started. Kids, we're going to get started. So everyone is here. This is going to be the final vectors seminar that we're going to be giving. Starting next week, if you read the D2L announcements, we're going to be starting our unit 5, 6, basically the topic that will be for the next 3 vectors, 5, 6, 7, 8, which will be derivatives. So this is the last time I'm going to be tackling vectors. This is also the strategies in this seminar is what you're going to be using exclusively for the Unit 4 guide, okay? So what you learn in this seminar should not be used for force and vectors. Those are geometric vectors for Unit 3. Now we're going to move on to algebraic vectors. So I'm just going to give you a second to copy a little bit into your study notes about the definition of Cartesian and algebraic vectors. We're thinking about giving you a unit for your study notes at the end of the year, kind of like a notebook check. For those of you who are making really good study notes, giving you credit for that. So let's start off by defining Cartesian. So algebraic vectors and Cartesian vectors are the same thing. You'll hear me referring to both by both names. Oh, I'm recording this. So I started off with a brief blurb that I just want for the video about René Descartes, who is a famous mathematician.
Pardon this interruption. Was Salvador Ramon Miranda, please report to room 129.
And he was the first to point out that you can combine algebra and geometry through a coordinate system. So force and velocity, we were doing a lot of the tip-to-tail strategy, drawings, position diagrams, vector diagrams, tension problems related to physics and other sciences. That is essential for Unit 2. You need detailed diagrams, you need detailed steps. Sometimes when I'm checking student work on my consultations, I'll see the formula and the answer. That's not enough, kids, especially because we're taking out the test. We need you to give us detailed steps, all right? For algebraic vectors, the steps are a little bit more simplified. That's why I really want to stress the strategies in this seminar can only deal with Cartesian algebraic vectors because we're talking about a coordinate system and we're translating our vectors to become position vectors. It's definitely a different topic from Unit 3. This is exclusively the strategies for Unit 4. So I'll give you a second to copy that down, and we're going to pair a diagram. So I'm going to show you a vector that has endpoints Q and R. We identify the vector, so you'll say QR with the vector sign over it, as a Cartesian vector because its endpoints can be defined using Cartesian coordinates, so X, Y coordinates. In this seminar, we're going to be talking about X components, Y components, and how we can solve for the resultant in a different way from the strategies that we learned in Unit 3. This is going to be a much more simplified way. Usually in previous years, there was a triple unit test after this on vectors, lines, and planes. It's a whole different concept. We've moved this concept to the end of the course because that is something that is not absolutely essential for first year calculus. So we're trying to teach the essential components first. If we get to those units at the end of the course, we'll be revisiting algebraic vectors later on. So unlike limits, when I said we're leaving limits behind, we're not going back, there is a possibility we will be going back to algebraic vectors later on in the course, but we will be taking a break from vectors for 5, 6, and 7, okay? Another important thing that I want to point out, when we're talking about vectors in this unit, algebraic vectors, and specifically position vectors, when we're talking about a vector, I want you to use square brackets. And when we're talking about a point, a Cartesian point, that's when you use your normal brackets. Okay, so you'll see me over the course of the seminar distinguish between these two elements. So something I'm going to do a lot of is translating the vector so that its tail is at the origin and the tip is going to be at some point P, which we're going to represent by AB. But when we define the Cartesian vector as a position vector, I will use the coordinates of the tip and I will enclose them in square brackets. That's a strategy that I'm going to be using for multiple steps. So you see here, it says we were given this vector QR. I'm going to move the vector QR to the origin. So when I move it to the origin, the tip becomes very important. And we're going to be talking about that as a position vector. But let's get to some other elements. Resolving Cartesian vectors into unit vectors. In MCR, did you tackle unit vectors before a little bit? Okay, so this might be a brand new concept for some of you. The most common unit vectors, so unit vectors we talk about in 2-dimensional as well as 3-dimensional space. So if you can copy down in your notes, the most common unit vectors and the ones that we're going to be dealing with in this unit is the unit vector I and the unit vector J.
Please report to room 306. Please, Deanna Ling, report to room 306 now.
So in the notes in the seminar, vector I has this little vector sign. It also can be written with a hat or an upside down V. So I can write unit vectors like this. And the reason that I'm using the points 1, 0, if I look to my diagram, the point 1, 0 is on the x-axis. So the unit vector I, we're going to use that to talk about horizontal components. Some of you in physics might have learned this already. Whereas the unit vector J is defined as 0, 1. So that point lies on the y-axis. And we're going to be using unit vector J to demonstrate vertical components. So horizontal components and vertical components. So always note that our unit vectors, the vectors we talk about, they're starting at the origin and the end point, this is the end points of the position vectors that I've written down. I also want to give you a second to write some definitions about unit vector and their magnitude. So basically what this is saying is that we can multiply our unit vectors by a scalar number and represent other vectors according to by unit vectors. Okay, so we can use the definition of unit vectors.
Professor Edwards and Gray Hunter, please report to English. Professor Edwards and Gray Hunter, report to English now. Hold that down, 6004.
So something I want you to write in your notes, since we have horizontal and vertical components now of these unit vectors, we can translate any vector that you are given in this unit into horizontal and vertical components. And I'm going to do a problem of that represents that. So for example, this vector OP. we can see that OP is represented by x is equal to 3, it looks like, and y is equal to 2. That is the point that is at the tip of the vector. So in terms of horizontal components, I can illustrate my unit vector by multiples along the horizontal, multiples of I, as well as multiples of j. So in general, I'm going to write down OP. Oh, and here's a definition here. OP can be illustrated by a scalar vector times I plus that's horizontally, and a scalar vector times j. And we can illustrate the resultant or the position vector OP using that formula. So this is just getting used to some definitions of position vectors. So always remember that, don't want to mix this up, A represents multiples of unit vector I. And I want to use another color here. B is going to represent multiples of unit vector j. Okay. But unless we do some real problems, this is all just generalized right now. You're going to find that there are not so much need to draw diagrams in this unit, but we will be using the definitions, the formulas, and just point coordinates and position vectors to help solve for the questions. Okay, so a perfect question would be something like this. Practice representing vectors in 2 equivalent forms. So we have 4 position vectors here. This is what the diagram looks like. So I have 4 different position vectors. Notice that they are defined by the point where their tip lies. Okay, so if you can write all 4 of those down. And I'm going to start with OP. So it says here that the position vector OP is defined by my square bracket 1, 2. I want to now write each of these vectors using unit vectors. Okay, so I'm going to use my definition AI plus BJ. Right? So my horizontal component, my scalar is going to be 1. So instead of 1, I'm replacing 1 for A. So that's going to be the same as 1I, or just I by itself, plus, instead of my B value, I'm going to be replacing that with the number 2. So that should tell me that I can represent OP plus I as I plus 2j, the unit vector I plus 2j. And if I look at OP, I can see that I need 1 unit vector horizontally and 2 unit vectors vertically in order to get from the origin to the tip. And that's what we're kind of mapping out. How many unit vectors do we need? How can we break up that position vector into horizontal and vertical components? Now for the next question, -3, 0. There is a horizontal component. There are no vertical components. So I want you to take a second and try each of these. And we're going to see if your answers match my answers. Okay, so take a second and try to break these up into horizontal and vertical components. Let's zoom in a little bit more. Nope, that's enough. Trying to make this a little bit bigger and it's not letting me. Screen. Sorry, kids. Okay, so for the first part, -3 is our horizontal component. We should have -3i. And what are we going to write for our vertical component? Are we going to write anything there? No, we're not going to write anything. So you should have just -3i. We're breaking it up into using our unit vectors. For OR, I know I definitely have horizontal components and vertical components. So you have -4 should be your number in front of the I. -1 should be the number in front of the J, or the coefficient in front of the J. And finally, OS is 2i minus j. So that is one way of representing Cartesian algebraic vectors. But you could, if we were going to test you, of course, we could also give you this question over here. If you are given the vectors that are written using unit vectors, so we have OA is equal to -i, OB is equal to I plus 5j, and OC is equal to -5i plus 2j. All you would have to do is take those A and B terms and write them in component form. So remember, component form has to have square brackets, and you have to have your A and B terms. What does that A and B represent? What point does that represent? Does it represent the tail or the tip? Can anyone tell me? The tail of the vector or the tip of the vector? Does anyone know? So it always represents the tip of the vector. So if I have just -i by itself, that means I only have a horizontal component. And if I look at my actual diagram here, oh, okay, those are not illustrated. But for the vectors over here, each of these points represent the tip. And if I were writing them when we were given them in component forms, those points that are at the tip are actually written in enclosed brackets, and that makes them algebraic vectors in component form, okay? So for the next question, when we are being given the vectors in unit vector form, we just have to remember that this also is a way of illustrating how to break up the horizontal and vertical components in order to get from the origin to the tip, right, of the vector. So we're taking these coefficients, there's a 1 in front of the I and a 5 in front of the J, so I'm enclosing that in square brackets with my horizontal component going first and my vertical component going second. So what would OC be? How would I illustrate OC as in component form? Janet? Yes, thank you. -5, 2 enclosed in square bracket. Okay. Very, very simple. We're always talking about the tip of our vector, and we call that our position vectors. So another way of saying the definition that I gave you first, and maybe I just want to go back to that. I'll zoom out a little bit. So if we go back to the previous slide, the position vector OP can be represented as OP is equal to square brackets A and B, A comma B, or OP is equal to AI plus BJ, where 0, 0 is the origin and point AB is any point on the plane. So what we can say here, A and B are scalar multiples of the x and y coordinates of the tip of the vector. Okay, so they're scalar multiples of the x and y coordinates of the tip of the vector. That's another way of redefining or rewording this definition. A and B are scalar multiples of the tip of the vector, okay? Yes? Okay, so now we're going to use this information to go into some other concepts. And remember, I'm going to post all of this so you're not missing anything. Okay, magnitude of vectors. Do you want me to go back to that one?
Sorry, the
Yeah.
tip of the what?
The tip of the vector.
Oh.
Okay, so A and B are scalar multiples of the x and y coordinates of the tip of the vector. Okay. I want to give you a second to write this down, the magnitude of vectors. So because in Cartesian form, our tail is always going to start at 0, 0. Boys, are you listening to the seminar or are you just working on other stuff? You're taking notes? Okay, good. Since we're always having our tail at 0, 0 at the origin, and we have our tip of the vector at a point in the Cartesian system, we're going to use always, 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 no other formula except trigonometry, and that is the formula that we've been using sometimes in Unit 2. We only get to use trigonometry or the Pythagorean theorem sometimes because we're dealing with all 4 quadrants, but this is our standard formula, so just write that down. And now we're going to talk about how adding and subtracting vectors in this world, in the algebraic Cartesian world, is a lot easier now. Before we had to redraw vectors from tail to tip or tip to tip, you had to figure out the proper strategy to use. Now, because again, our tail is always starting at the origin, it's going to be a lot easier and you don't have to draw out your vectors for this particular unit, for Unit 4. Okay, so before we do that, find the magnitude of my position vector 7, 4. Okay, so a few things I want to go over in terms of terminology, okay? Do we know what we call the angle if we're moving from the x-axis to this vector? Does anyone know from physics what we kind of call the arm of this vector? Does anybody know? Starts with the letter T. Okay, so if this is our position vector, yes. Terminal arm, very good. So we're always going to be solving for theta from the x-axis to the terminal arm. That's going to be very important. If you're just calculating the magnitude, that's for theta. Magnitude, obviously, is the distance of that vector. We're just going to be substituting it into the formula. So taking the square root of 7 squared plus 4 squared, because those are the the components of my tip of my vector. Does anyone have any questions in hearing some talking? You're just taking 7 and 4, plugging it into the Pythagorean theorem. Square root of that, you get square root of 65. Now, every longer question that I'm going to do with you, there's going to be calculating the magnitude as well as finding the sum of the resultant. We're still figuring out the resultant in many cases. It's just a lot easier than before. Okay. Now, finally, adding and subtracting vectors. I want to give you time to write this down. Can everyone write this down, please? So I have a vector v, 7, 4, enclosed in square brackets because it's in component form. My vector u, so this is not talking about unit vectors. I have 2 different vectors. My vector u is in blue. My vector v is in red. Now, in the previous unit, these 2 vectors are being displayed tip to tip. We have to either figure out how to translate them or use the parallelogram method in order to find the resultant. You don't have to do that for this particular unit. It's still good practice to, if there's a diagram in your unit work, please draw the diagram in, if there's a diagram in the textbook question, please draw it in your unit work. That way it helps your teachers when we're assessing your work. We also really don't want to just see answers. We want to see you write out the questions, kids. And if there's a diagram included, please do that so we don't have to send you back. But this time we don't have to rearrange and we don't have to solve using a diagram. Basically, within your square brackets, you're going to be adding your horizontal components. So 7 plus 2, that's my horizontal component. My vertical component of each vector is 4 and 6. So I'm going to add those. And that gives me the point, the tip of my resultant. So if I even drew it the old way, my resultant would be at this point 9, 10. But just by using the formula, this formula up here, adding your x components, adding your y components. That's what the formula in your textbook and your unit work means. And that's all you have to do. But please don't just write the question and write the final answer. Include the step that helped you get the answer. But you see that's very, very simple. So we can use coordinates we can use coordinates algebraically to define the sum and differences of vectors. So there is no need for repositioning any of your vectors. Let's move on to another example. Okay, this is a subtraction problem. And if we look at the diagram of these 2 vectors, again, we have vector v that is at the origin. We have vector u that is at the origin, right? So usually I would have to rearrange these to figure out the resultant. But in this particular case, we're subtracting. All I have to do is, according to the formula, subtract my horizontal components, subtract my vertical components. So my answer is going to represent the tip of my resultant. And actually, because these are not tip to tail, we would have had to use the parallelogram method, and that would have given us this point, the resultant of 5, -2. But instead of using the diagram, we're using our formula, and the concepts of horizontal and vertical components. Again, this is not the strategy that you're using for Unit 3 because Unit 3 is about geometric vectors. But we can solve some problems, and I will solve a problem at the end that's similar to something you encountered with geometric vectors, but we're going to be solving it using algebraic vectors. So far, very simple. We are going to get to a challenging question, but we need to lay the foundation for that challenging question. So that's why everything looks very simple. The final concept is multiplying a vector by a scalar. So for example, the question is saying, if vector v is equal to in component form 7, 4, find 2 times vector v. So what the question is asking us, if this is vector v, I want to have 2 of that vector v, but we have to be going in the same direction. All we're doing is doubling the magnitude. So it makes sense, if we're going to double the magnitude, we have to double the x component as well as the horizontal component and the vertical component. We have to double the horizontal component and the vertical component in order to get in component form what the new tip of the vector is going to be. And that point will be x is equal to 14, y is equal to positive 8. That will be the tip of the new vector. Okay, still very, very simple. Everything makes sense. We're laying the foundation for a question that involves scalar multiples, but it is a bit complex, okay? So we're getting to a more complicated question, I promise. Before we get to that complicated question, we have to write a definition that is going to follow us for the whole course. Okay, so let me zoom out a little bit. Okay, can we all write this in our notes? 2 vectors that are collinear can be drawn so they lie on the same line. In other words, they are scalar multiples of one another. So you did something similar in MCR without knowing that it was going to prepare you for collinear vectors. But we have to, and you might remember from MCR, if you had to prove something was scalar multiples of each other, if you have to prove that, how would you tackle a question like this? So far our vectors have looked clean and nice, very small numbers. I'm going to give you a vector, 2 vectors with some fractions, and we are going to prove that they are collinear, which means you can draw the 2 vectors on the same line. So that concept of being collinear, which you might not have encountered before, you're going to have to refer to in this course as well as your first year calculus course. So what we're going to do in the next question, we're going to check that there is some scale factor. The scale factor would be k. Actually, let me give you the question first. Okay, can I move to the next slide? Yes, great. So let's write down this question because the vectors are quite complicated. I will zoom in even more. There we go. So our vector u with defined as 3. My horizontal component is 3. My vertical component is 5/6. And vector v, where my horizontal component is -3/2, and the vertical component is -5/12, are they collinear? So when the question is asking, are they collinear, we have to check that there is some type of scale factor that keeps the ratio from the x coordinates the same to the ratio from the y coordinates. That's what the formula you copied down on the last slide meant. The ratio of the x coordinates will be the same as the ratio of the y coordinates. But how can we do this? So let's start off with a definition. My ratio of, vector u is going to we're going to prove that it's going to be equal to vector v multiplied by some scale component k, scale factor k. That's what we're trying to prove here. And this might refresh some memories from MCR. So how I'm going to set that up first is to write out my vectors. So my vector u with the coordinates, the component form of vector u has to be equal to k times, in square brackets, my component form of vector v. Does anyone have any idea what the next step might be? What should I do next? Any idea? If that k is in front and I have to multiply it, what is that called? What did we learn in grade 9? Something? Yes, we're going to use our distributive property. First of all, we're going to use our distributive property and multiply, because the x component of vector v and the y component of vector v have to be multiplied by some scale factor, and then that has to be equal to my vector u. That's what I'm trying to say, okay? So now, that's as far as we can go in terms of those components. I want you to draw a line in your notes, and now we're going to resort to algebra. We're going to set up two algebraic equations, okay? So first of all, to solve for the scale factor just using my horizontal components. So I'm going to say 3 has to be equal to -3 over 2k, right? If I cross multiply, so let me use my highlighter. If I cross multiply the 2 and the 3, that's going to give me 6 is equal to -3k. If I'm trying to isolate k by itself, that means I have to divide both sides by -3, and that gives me my scale factor k is equal to -2. Okay, I haven't proven anything yet. I've just proven that in order for my statement to be true, in order for the vectors to be collinear, in terms of the x components, the scale factor has to be k. We're going to see if the same is true for the y components. If it is, that means that the two vectors are in fact collinear. So again, now I'm going to set the y component. If I go up here, the y component of vector u, I'm going to set that equal to the y component of vector v multiplied by a scale factor of k. This is a little bit more complex because now I have to multiply 5 and 12. I have to multiply 5 and 12 together. This is cross multiplying. 6 and -5. Everyone should be well versed. Sorry, not just -5, but -5k. So I'm cross multiplying because I have two fractions separated by an equal sign. That gives me 60 is equal to -30k. I want k by itself. I don't want this -30. So what do I have to do to both sides? What do I have to do? Something? Divide both sides. Thank you. Divide both sides by -30. So that gives me a final answer that k is equal to -2. Okay, I gave you an easier method of doing this. There is also a different method that I'm going to include in the notes, but It is more complicated to understand because it involves setting up your vectors as ratios, and it involves a fraction divided by a fraction. So I thought that was a little bit more confusing, but our concluding sentence is the same. Our strategies are still the same. -2 is equal to -2. So that means vector u is equal to -2 times vector v. Therefore, and I want you to include this in your notes, and therefore u and v, vectors u and v are collinear. That's the statement you would make at the very end. Okay, one more rule, and then we're going to jump into and end off the lesson with a more complicated algebraic vector type question. But running out of time, so all you have to do is understand this concept and maybe write down this formula in your notes. So when we're talking about a Cartesian vector between 2 points, we can solve for that. What if we can translate the vector to the origin and figure out the difference of x coordinates and the difference of our y coordinates. The order of subtraction is very important. So when you're figuring it out in component form, you can't take the x coordinate of your tail and subtract the x coordinate of your tip. It's very important that you always take the x coordinate of your tip minus the x coordinate of your tail, the y coordinate of your tip minus the y coordinate of your tail. Okay, that's the final concept I'm defining in this seminar. But I do want to make sure that we have time, especially because I'm recording, to talk about geometric vectors in Cartesian form. So if we are given a geometric vector, how can we rewrite this as a Cartesian vector? Okay, so some problems I wasn't expecting. So, okay, just based off the last formula, some really easy stuff here. If we have 2 vectors and I'm trying to figure, so 2 separate points, and I'm trying to figure out how to write vector B, A, B in component form, I'm going to take the x coordinate of my tip, my tail, no, I meant to say my tip, and I'm subtracting the x coordinate of my tail, the y coordinate of my tip, minus my y coordinate of my tail. So I'm going to include these in the notes. It's just illustrating that last formula, taking the x coordinate of the tip minus the x coordinate of the tail, the y coordinate of the tip, and subtracting the y coordinate of the tail. Once we have that vector in component form, we can use the magnitude formula to solve for the magnitude of that vector. So very straightforward, very simple, but I want to move on to a word problem. So there are 3 examples, I believe. So points C and D are also defined. If I take my x coordinate of my tail tip and subtract my x coordinate of my tail, my y coordinate of my tip, subtract my y coordinate of my tail, I can define vector CD in component form, and using that vector, I can then substitute it into the magnitude formula. Okay, to finish off, can we write this problem down? Sorry, I lied. There's 2 problems, but we need to know this first. Write a force of 200 newtons at 20 degrees to the horizontal in Cartesian form. Okay, so I have this vector, which is 200 newtons. 20 degrees to the horizontal. I've drawn that in. And if we're going to write this in Cartesian form, I know that this is my reference angle. Cos theta would be equal to my adjacent over vector v. And that is actually up here, so I should have given the formula first. So my adjacent is defined as, if I'm solving for my adjacent, magnitude of v times cos theta. Okay, I know my magnitude of vector v in this question, 200 newtons. I know the angle theta, so my adjacent can be defined as 200 cos 20 degrees. That is my horizontal component. My vertical component wouldn't be defined as cos, but it would actually be the opposite, right, over vector v. So I could define my vertical component as 200 times sine 20. So to solve for my force vector, it says to write a force of 200 newtons at 22 degrees to the horizontal in Cartesian form. The formula that we're going to use for the more complex problems is going to be the magnitude of that vector, in this case my force vector, multiplied by cos theta, where theta represents my principal angle. And the principal angle, remember, I defined is from the x-axis to the terminal arm. That is our principal vector. The vertical component will be the magnitude of F. In this case, I know the magnitude of F is 200 newtons times sine theta. We're going to reuse that formula over and over again. Okay, so this is when I know my principal angle and I know the magnitude of my vectors. I can write a vector in Cartesian form by simply figuring out what 200 times cos 20 degrees, 200 times sine 20 degrees, and that gives me 187.9 and 68.4. That's my horizontal component and my vertical component, and that helps me illustrate the vector in Cartesian form. Now I'm going to use this concept and this formula to define the very last problem in this seminar, which is going to be a more complicated problem, very similar to what we did with force and velocity in the last unit. So you don't have to write out the whole question, but please try to draw the diagram so you're not getting lost with what I'm doing and you're understanding what I'm doing. So I have two sets of vectors in this question. A ship's course is set to travel at 23 kilometers per hour relative to the water on a heading of 40 degrees. And that's 40 degrees from north, clockwise, right? A heading of 40 degrees. We know that is going to be the angle from north, clockwise. It says a current of 8 kilometers per hour is flowing from a bearing of 160 degrees. So we're going to deal with both vectors separately. Don't worry about copying the whole question. We want to draw out these vectors in Cartesian form. So it says write each vector as a Cartesian algebraic vector. We're going to start off with the ship's speed. We know the magnitude of that ship's speed is 23 kilometers per hour. So that will be the magnitude of this vector. We are given that relative to the water, it's set to travel on a heading of 40 degrees. So 40 degrees is from north to the terminal arm, but that is not going to be my theta. When I'm trying to write my vector as a Cartesian vector, and I'll highlight that in a second, I do need to figure out the vector from the x-axis to the terminal arm, okay? So we cannot use 40 degrees as our theta. We have to use this angle 50 degrees because that is my principal angle from the x-axis to the terminal arm. Can everyone write that down? Your principal angle theta has to always be from the x-axis to the terminal arm. And that's important because now when I'm plugging that information into my formula, I have the magnitude times cos 50, because cos 50 degrees is my principal angle, and I have the horizontal component will be the magnitude, 23 kilometers per hour, times sine of my principal angle, okay? If I use the angle that they gave me in the word problem, I won't have the correct answer. And obviously we have to simplify that a little further. We can, let's see. You can actually punch that into your calculator to get exact values, but I'm not going to do that yet because in order to get the resultant, so have these two, figure out how these vectors play with each other, I have to now work on the next vector. This is all of it, but way too complicated to look at the solution like that, so I'm going to break it down. So we're trying to find the velocity of the water. This is the vector that we're given, and we're told from north to the vector, because if we look at the original problem, it says a current of 8 kilometers per hour is flowing from a bearing of 160 degrees. So if we translate that from north, it's a bearing of 160 degrees. That's what it looks like based on the problem. But all algebraic vectors have to be repositioned. So we have to reposition this vector at the origin. So if we're going to do that, it's going to look like this, taking this vector and moving it to the origin. Now I'm just going to go back for 1 second. I know this whole angle is 160 degrees, but if I'm just looking for this part, that's going to be 90 degrees plus some angle theta. So 90 degrees plus 70 degrees gives me 160 degrees. That leaves me with 20 degrees in here. Now when I reposition my vector, that 20 degrees, according to the law of opposite angles, this 20 degrees is going to be the same as this angle over here. Does everyone see that? Okay, so I'm now just worrying about this angle, but I'm using the information that I've been given to figure out what the important angles that I need to know for this particular question. Okay, the next step is we have to define the principal angle. If I know this is 20 degrees, and remember my definition of the principal angle is I want to know the angle from the x-axis to the terminal arm, from the x-axis to the terminal arm. The number of degrees in this quadrant is 90 degrees. If we add the extra 20 degrees, that gives us our principal angle is 110 degrees. So if you can, please draw that diagram and this definition into your notes. So for Cartesian vectors, the principal angle is the angle between the x-axis and the terminal arm. So we've, by repositioning the vectors and then analyzing the angles carefully, we've figured out that the principal angle is 90 degrees plus 20 degrees, which is equal to 110 degrees. So to figure out the algebraic, how to write this as an algebraic or Cartesian vector, I do have to write this as the magnitude of W times cos theta, comma, the magnitude of W times sine theta. I know what theta is, and if I read the problem carefully, it said a current of 8 kilometers per hour. So that means my magnitude is 8. So I could write this vector as 8 cos 110 degrees and 8 sine 110 degrees. Yes. Oh, no questions here, right? So now we take this very complicated solution that I had written initially, and I've broken it down to make some sense. So I've broken it down to have the angles make sense. So last part, I swear, we have our W, we have our vector S. So in order, instead of positioning things from tail to tail, tip to tail, whatever you wanted to do, this time it's very easy to determine the resultant velocity of the ship. All I have to do is take my vector S, which was, what did we say? That was the ship's speed, and my vector W, which is the velocity of the water, and we're adding those two, all those components together. So my resultant is now an actual value based on that formula. And someone asked me the other day, this little squiggly line on the top just mean that it's an approximate value. It's not an exact value. We've had to round that a little bit. So that's an approximate value. We can, and that is the position vector of the resultant. We still need to figure out the magnitude of the resultant by plugging it into my magnitude formula. And the final component of this question would be to use trigonometry to solve for the direction of this vector. So because I have my resultant, I know what my horizontal component and my vertical component is. This time we're not talking about principal angles. We're just trying to figure out the angle, the direction from north to the resultant. So I can use opposite over adjacent. I can use my tan formula, and that will give me my final answer that the ship is traveling at a velocity of about 27.875 kilometers per hour at a bearing of 25.6 degrees. Sorry to rush that last part, but you are going to encounter word problems like this. And I just want you to be clear that you can solve this in Unit 4 with the methods for algebraic and Cartesian vectors. Just before you go, kids,